0, and I will branch out when x is equal to 0 to stay where I am, or when x is equal to 1, I go to state 1, and when I am at 1, if x is 0, I go to 1, 1, if x is 1, I go or I stay in 0, 1, and so on. So this tells me exactly the behavior of the circuit in time, and I have also determined the value of z. Now, so now to analyze the circuit just in terms of behavior, okay, when y1 is equal to 0 and small y2 is equal to 0, I go to state A. If y1 is equal to 1 and y2 is equal to 1, then I go to state C and so on. So here what I am trying to do is to look at these states and present them by state variables. So we went the opposite because this is analysis by assigning y1 0 and y2 0 as A, y1 1 and y2 1 as C, y1 1, y2 1 is B, and y1 1 and y2 0 is D. So these are my state variable coding that I have, and I coded them backwards to state names. So now instead of talking about state 0, 0, I talk about the state A and so on. So this is what we call the flow table. So we went from the state codes into flow table. When we do design, we go from flow table to state variables. So the state table with outputs, as you can see here, I might ask you in the exam to analyze the circuit down to the flow table, which means you cannot stop at big Y's and small Y's. You will have to take it to a state coding, which is give the state some names, and that's what we are doing here. So from A we go to A rather than from 0, 0 we go to 0, 0. From A we go to B rather than from 0, 0 we go to 0, 1 and so on. So that's what we have here. And it gives me the output too. So I consider this to be your ultimate goal of analyzing a circuit, to determine its behavior time-wise and also the output it produces at a given state. So now because we have used state naming as A, B, C, D, now we can create a state diagram if needed. So if I ask you to come up with a state diagram, you just have to look at A going to A when x is equal to 0, A is going to A when x is equal to 0, when x is equal to 1, then it goes to B, when it is in B, x is equal to 1, stays, and it produces 0 and so on, okay? So that's the basic idea here, analyzing a synchronous circuit from the circuit level back to the state diagram and state table. Is there any question here? Anything surprising, any topic surprising here? Anything concerning, difficult? You know this material already and it's fine. Okay, that's good. Any question there? Yes?
D is a dead state. Why did you include it just for...
Huh?
I said, why did you include D as a dead state?
Why did I include?
D?
Yes?
If it's a dead state. What input combination would leave?
Yeah, that's a very good question. So this is a dead state. Why? It means if we are in it, we can only go outside, but we cannot come to it. Many machines, we design them so that the D state is the state where you start your machine, which is like an initial state, and everything else becomes the behavior of the circuit. So when you look at the table here, when you look at D, it goes from D to A or D to B, but none of these states go to D. So therefore, you never go to D, but if you happen to be in D, you can only go to A, B, and so on. So it's like a booting state, you know, like a state where you can get your system to start and you go from there. Now, design. The design starts from a problem statement. We need to understand the problem. If you understand the problem, the rest is mechanical, straightforward. So let us take a design example here, which is similar to something that you have done in the past. We would like to design a controller of some traffic lights that control intersection of two roads, okay? One goes north, south, and the other one east, west. but we'd like to allow people to cross whenever there is a need for them to cross the street. Okay, so we'll operate the traffic light as if nobody's there. There is people crossing the street, but when somebody wants to cross the street, he or she has to press a button, and then the button will allow the system to give them the green light to cross the street when it is safe, after we stop the car traffic. So normally, this is the statement, normally the lights sequence between north-south and east-west. If a pedestrian presses a request button, P, then the north-south and east-west will go red, and the lights will go green for the person, so then he or she can cross the street. So what are the possible states? If you look at a traffic light, this is how you should think about it. We have the traffic, this is a state where I look at the traffic and it is allowing people to go north-south. Or it is allowing people to go east-west, or it is allowing the person to cross the street. So when we allow people to cross the street, we allow them to cross the street all over. So it's not only one segment. So the traffic light is not very sophisticated. So as you can see, when we are in north-south, we are going to make sure that the green signal for north-south is green, and the red signal is 0, okay, which is not on, and the east-west green is not on, and the east-west red is not on, and the crossing sign or light is not on, and the stop, telling people to stop, is on, okay? We do the same thing here for the east-west. And then when the person is to cross the street, and we would like to allow that, then we would have to set every other light to be red, and then the green light for the person is going to be that on, which is here indicated, and the stop signal is no longer active. So this one here, this table, just takes this statement. You may come up with a different table. You may come up with a different interpretation. And your design may not necessarily coincide with my design, which is okay. A design allows for some degrees of freedom. So it's okay for you to come up with something different than this. You don't have exactly to do something like this, but it has to tackle the problem. Yes?
So we're assuming there's only one pedestrian crossing?
That's right. Yeah. We are saying that if I am going to cross this road, I can cross the whole thing, like going around. So it's almost like allowing everybody to cross at that time. Stop traffic, no cars. Very simple traffic light, okay? So you may want to make it more sophisticated. So this is the statement. We are just building it here in a state diagram. So I have the north-south, and I have the east-west, and I have the person crossing here. So as you can see, is this a Mealy machine or a Moore machine? Mealy. As you can see, it's a Mealy machine. Why? Because we are not producing the output inside the statement. So what we are saying here, if nothing is pressed, P is not 0, is not pressed, which means there is no person wanting to cross the street. It doesn't matter. You just go from north, south, switch to east, west, okay? Which means you have this one to be green, this one to be red, and this one to be red, which is the person is not allowed to cross. Okay? When you reach this state here, now you are in the EW state, you wait for the clock, and then it doesn't matter if there is an input or not, you just have to go back to north, south. Okay? So 1 or 0, the system will just ignore it and come back to this state first. This is a design. You can come up with a different design. Okay? You can say, when I am here, I will allow the person to press a P and I can deal with it, which is okay. So don't take this to be one unique design that every one of you has to do something like that. Just understand the process here. So now I go back. Okay? So I go back here, and now I see the one pressed. That one now, and make sure that I go to this state.